Alright, so we're going to go ahead and complete our lecture on the topic of the Euler-Lagrange Equation. So we started this lecture on Monday, and this was the one that was supposed to take place in class yesterday, but we couldn't do it because of all those technical problems. Alright, more pages for you. So we are on the topic of the Euler-Lagrange equation, and in that we would write an expression, a very general expression for the sort of the thing that we're looking for. In this case, it's a path where y is a function of x. We know that there will be one for which whatever it is that we're interested in. So let's talk about that for just a moment. So let's say that this is the length of the path from x1 to x2 of x. The derivative of y with respect to x is y prime, and x is the independent variable, and we're going to integrate that over dx. Alright, so that is going to be an integral over a function, and we would like to know where that has a minimum, so we'd like the minimum length. So what we would do is we would consider a nearby path, which would be equal to the minimum path that we're interested in, plus perhaps some other function of x. So we're just sort of adding those to this, the black line, plus some function eta, which is the difference between the red line and the black line. And when I add them up, that will be equal to capital Y. Alright, that's fine. And we notice that eta at x1 and eta at x2 must be equal to 0. So in order for it to be a path from 1 to 2. Then we're going to, that's a fine definition for capital Y, but then we're going to change it, we're going to tweak it, now that we've defined this idea that there could be this function, and indeed it could be any function, so this is still a very arbitrary general statement. I'm going to imagine the case where I turn eta on with a constant alpha that can go from negative something to positive something, but it also goes through 0, and when it goes through 0, the capital Y will be equal to the lowercase y. Alright, so that is what I am looking to do here, so that I can turn on this alpha, and that it will go through a value for which my integral will be its minimum. Okay. Alright, and so now my integral for an arbitrary path is going to be a function of this capital Y and capital Y prime, which is the red curve. Notice that that is a function of alpha and eta. And x, and I made my substitution for capital Y and capital Y prime. And then I notice that if I want to write the derivative of this function, which is the argument of my integral, with respect to alpha, that it will go through 0 when this function is equal to the path that gives me my minimum here. Alright, because this will go through minimum when the argument of this integral goes through minimum as well. Alright, I guess what I'm saying is, as a result, the derivative of this left-hand side with respect to alpha will be equal to 0 when the derivative of this argument with respect to alpha is equal to 0. In that case, that's the only case in which these two can both be equal to 0 arbitrarily, or generally. Okay, so I need to consider the derivative of this argument here, and when I do that, I notice that I have these is now not a function of y prime and x, it's a function of something that I'm calling b, a and b and x. All right, and if I want to generally write the partial with respect to alpha, I notice that would be partial with respect to x times dx d alpha. X does not depend on alpha, so that's why that 0 is there. But that's true for any derivative of a function that depends on 3 different variables. Okay. And then I notice that I want to explore the area where alpha is small, in which case a will be equal to y, approximately. And dA d alpha is obviously equal to eta. Alright, so that's why we get df dy eta. Similarly, for this next term here, I would have df dB. In the case where alpha is small, b is going to become y prime. And dB d alpha is obviously going to be equal to eta prime, just from our expression for b there. Okay. So in the end, the expression that we get for the partial of alpha with respect to partial of f with respect to alpha is this expression here. Okay. Integral with respect to alpha, and in this case it's path length. And that must be equal to 0 when it goes through a minimum. And that is equal to, writing this out as an integral, I can just take my derivative with respect to alpha of the argument, and then I can make my substitution. Now this is where I want to pick up, because I want to look at this second term here, and I want to do some useful math with it. So what I'm going to do is I'm going to say recall integration by parts. All I mean is recall the phrase integration by parts, and I'm going to the sort of key to integration by parts is that u times v is equal to the integral of u dv plus the integral of v du. Alright, and I know my v's look a little bit like u's, so I apologize for that. But hopefully you can see the difference. And so I can sort of, and by the way, this is, I should note that this is when I evaluate it from, let's say, initial to final. This would be from initial to final, and these have to have the same limits as that guy on the left. Okay, so this is really the sort of defining statement whenever you want to use integration by parts. It means that you can do this integral by doing this integral instead and evaluating the two functions. So in this case, we're going to use integration by parts in the following form. So we're going to have the integration from initial to final of u dv, doing my best to make them look different there, is equal to u times v, evaluated from initial to final, minus the integral from initial to final of v du. Now, in this case, I can use that here because I can make the following substitutions. I'm going to let v be eta. I'm going to let u be df dy. And I think I needed a prime on this term here. Yes, I did. From there. So I'm going to let u be df dy prime. Okay. So in that case, dv dx is equal to eta prime, and du, okay, so that's what I needed here. Let me see what, make this substitution here. All right. That tells me that dv, which is something that I need to think about here, would be eta prime dx. And similarly, du will be equal to df dy prime, but I need to take the derivative with respect to x. So let me just go ahead and say du dx equals, so u is that. That would be d dx of u, where u is df dy prime. And if I just wanted du, which is what I want, I'll just multiply both sides by dx. So it's d dx of df dy prime times dx. All right, so now I'm ready to use these substitutions into my integration by parts. And what that tells me is that the integral of u dv, so df dy prime, times, so that is, hold on just a second, u there, dv is eta prime dx. That's great because that's actually the second term, the second integral here that I actually wanted. So looks so far so good. And that'll be integrated from x1 to x2. Alright, so now I've plugged in on the left-hand side. So we're working from here for our integration by parts, if you're wondering what I'm plugging into. Right? And that is equal to u times v, which I must evaluate from initial to final. So that is eta times df dy prime that I have to integrate from x1 to x2. Alright, minus, now I'm to this term v du, so the integral of v, so that's eta, times du, which is right here, d dx of df dy prime dx from x1 to x2. Alright, now this is the expression we want. This term right here, we need to remember that eta evaluated at x1 is equal to 0 and eta evaluated at x2 is equal to 0 because they have the same endpoints, all these arbitrary paths. So this must be 0. And I'll go ahead and make the note because eta at x1 equals eta at x2 equals 0. Alright? Let's just remind ourselves that was a condition that we put on the eta of x function. Alright. So now now that I'm sort of done with the integration by parts that I wanted, so I'm down to an expression that I wanted, and I want to put that expression into this line right here. Alright? So I have that 0, which is ds d alpha, so ds d alpha will equal 0 when df dy times eta let's go ahead and then I notice, you know what, this other term here, it's going to have an eta as well. So I'm just going to pull an eta out front of my integrand. Alright, so times the quantity, so I still have a df dy from before, and now I have this df dy prime eta prime, which is also equal to this, so I've got minus d dx of df dy prime. And that has to be integrated over dx. Now, the only way for this integral to be equal to 0 generally is if, because eta of x is not generally 0, is if this argument must be equal to 0. Alright? So in this case, I know that this condition is satisfied. When df dy minus d dx of df dy prime is equal to 0. Alright, so this is the Euler-Lagrange equation by which we can solve for the f of y prime, and x. Known here is f of, and we should remember that it's a function of y prime, and x. Alright, just to be clear, I'll write that there. So the only unknown in this equation is that function for which we have a minimum path, and we can solve it. So we're going to be doing that, but let's first go ahead and give this puppy his name. So we're going to be doing some applications. We're going to first find that shortest path between 2 points, and then we're going to do some other cool stuff. And I apologize.